Hello, welcome back. This is the last section for our polynomial unit. So you'll be taking another quiz on Wednesday. I'll probably leave it open for a couple of days for you again, just to help out with the scheduling. And then that'll wrap up, again, the polynomial unit. Then we'll start our last unit on logs and exponentials, and that'll be it before the final exam. And then hopefully by the end of the week I'll have a review for that final exam for you as well. Okay, so for today we're going to be looking at polynomial functions, more of a generalization of characteristics of polynomial functions. There are lots of things that we should be able to tell about the equation for the function if we're given the graph, or the graph of the function should tell us things about the equation. So let's talk about some of those characteristics. First of all, when you're looking at a graph, how are you going to know if that graph represents a polynomial function? A polynomial function, when you're looking at its graph, these graphs are going to be smooth, they're going to be unbroken, and they're going to be continuous. Okay, so what you would not see in a polynomial, the graph of a polynomial function, is a spike. No spikes, because you have to have a smooth graph. No gaps. It's got to be continuous or unbroken, and then no endpoints. Okay, if you see any spikes, gaps, or endpoints, that means you do not have a smooth, unbroken, continuous curve. It means you do not have a polynomial function. So number one is a very clear example of a polynomial function. So let's just say yes here. Hopefully we know what number two, the second graph here, is. The V-shaped graph is actually produced by an absolute value, but the fact that there's a spike there tells me that this is not a polynomial function. So this is a no, because there's a spike in the graph. And hopefully we knew that this was an absolute value function. The third one, there's a gap in the pieces of the graph here. We don't have one continuous graph, we have one piece separated by another. And that gap tells me again that this is not a polynomial function. So this is a no. And in fact, hopefully you knew that this was the graph of a rational function. Hopefully you saw the oblique asymptote happening in there. This next one has an endpoint. So the endpoint on this graph tells me again this is not a polynomial function. This endpoint means the graph is not continuing in both, continuing in both directions here. It should have a domain that is infinite, going left and right forever. And I think we've sort of talked about this with domain before, but your polynomial function, like these guys are all examples of polynomial functions here. It doesn't matter what you plug in for x, you can raise any value to any power and add or subtract and multiply and all that stuff with it. There aren't going to be any restrictions. So you should have a graph that goes left and right forever. So that endpoint again says not a polynomial function. And again, you should have hopefully recognized this one as a radical function. And then the last one is definitely a polynomial function, right? It's going to be continuing left and right forever here. There are no gaps in anything, no spikes. It is a continuous, smooth, unbroken curve. Okay, and really there should have been arrows on these too. Okay, so those are some features of the graph. When you're looking at it, how would you be able to distinguish between a polynomial and something that isn't? Now, end behaviors are another feature I want to discuss with you, because they're patterns. So we're going to graph some of our parent rational functions here, although we should know what a few of these look like. Y equals x to the first. I'm hoping we know this. That's our parent linear function. Parent cubic function. I'm going to go ahead and put it in Desmos, just if you're not familiar. Obviously we know y equals x to the first. Okay, if I put in y equals x to the third power, then our graph looks like this. Okay, if I change that third power to a fifth power, it just looks a little narrower. And if I was to change it to a seventh power, narrower, a ninth power, narrower, an 11th power, even narrower. Or that, we call this point here at the origin, we call it an inflection point, where it's not changing direction. That graph is increasing the entire way, but it just slows down as we cross the x-axis. As that inflection point gets flatter, the degree of the polynomial is getting larger. And I think we saw that before with one of the sets of notes we looked at in this unit. So all of these functions have something in common, and that is, again, their end behaviors. If we look at the left end of each of these graphs, all of the left ends are going down forever toward negative infinity. Every single one of them, and that's going to be true every single time you have an odd degreed polynomial. And if you look at the right end of the graph, all of these right ends are going up forever toward positive infinity. Okay, that's true for all, again, of our odd polynomial functions, odd degrees. So if the degree is odd, then the graph, it falls as we go to the left. It means it's going toward negative infinity. And it rises as we go to the right, which means it's going toward positive infinity. Okay? Now what about if the degree is even? Then we should know what y equals x squared looks like. That is our parabola. Well, what happens if we make it an x to the fourth? So x squared, there's our parabola. Make it an x to the fourth, it's a narrower parabola. A sixth is even narrower. An eighth, even narrower, okay? So again, the vertex, it looks like it's flattening out there. So this is a narrower parabola, and even narrower with a flatter vertex parabola, okay? But again, the end behaviors are the same. No matter what, the left end and the right end are both going up. Left and right end go up. Left and right end go up. So anytime we have an even degree, when our parent is an even degree, then the graph rises in both directions. Rises left and rises right. And so that helps us when we're looking at, like, this function here. This one we said was definitely a polynomial function. Now I know when I'm looking at this, because these end behaviors match, that this had to be an even degreed function, right? It had to be an x to the fourth or an x to the sixth or something with an even degree, because both of those ends are going up. And then likewise with, oops, I think I just erased my work here. Ay, guys. Set endpoint. I swiped and I had my eraser on. This was a gap in here, no good. Okay, so over here, this polynomial function, the fact that this side is falling and this side is rising or going down and going up, tells me that this had to be a polynomial function with an odd degree. So an x to the third or x to the fifth or something odd, okay? All right, so let's look some more here. The end behaviors will change with a transformation. Hopefully we know that transformation. If we stuck a negative in front of any of those, then the end behaviors would reverse, right? If I put a negative in front of the x squared, then our parabola would be upside down, so then both directions would go down toward negative infinity. That's going to be true every time. So if we put a negative in front of the first term, it reverses the end behaviors. So if I ask you for the end behaviors for a function, while you could absolutely put the function in Desmos and look at the graph, you should be able to determine these end behaviors without going to a graph, based on the parent function and the leading coefficient. So I could put it in Desmos, but I know this is my parent function, and the number in front here is positive. And x to the third does the same thing x to the first does. It rises to the right and it falls to the left. So as x goes to positive infinity, that is when I followed to the right, this graph is going up toward positive infinity. And as x goes to negative infinity, that's to the left. The left end of the graph goes down toward negative infinity. And that could be confirmed. Again, let me just to show you. If you put it in Desmos, 2x to the third minus 5x plus 1. There it is. We can see the left end of the graph going down forever. We can see the right end of the graph going up forever. But again, something we should know just by looking at the parent function. So same thing here. Okay, the parent in this one is our x to the fourth. And the fact that we have a positive 5 out in front tells me this graph is going to do the same thing the x to the fourth graph did. It's the same thing the x to the squared, or x to the second did. It's going to be some sort of a parabola where both ends go up. So as we go to the left or to the right, the graph is going to go up forever toward positive infinity. Okay? Here, our parent function is an x to the 5th. That's odd. Now, normally, it would be doing something like this, where it falls and it rises. But because we have a negative here, this negative reverses it, so our graph is going to be going down. So to the left, it's going to go up, and to the right, it's going to go down. So as x goes to positive infinity, that is to the right, this graph is now going down forever. And as we go to the left, it's going up forever. So our end behaviors were reversed. And again, if you weren't sure, just put it in Desmos. Okay, just put the function in Desmos, so you're going to see it. Negative 6x to the 5th minus 5x to the 4th plus x squared minus x. And there it is. As we follow the right end of the graph, it's going down. Follow the left end of the graph, it's going up. Okay, last one. Again, parent function here is an x to the 8th. That's going to be just like the x squared. That's going to be a parabola type of deal where both ends go up. But because it's a negative out here, that reflects it over the x-axis, which means now we have a graph that's going to be going down in both directions. So both ends are going to be headed down. Okay, so we're looking at the degree, the highest exponent, that's the parent function. And then we're looking at the sign of the leading coefficient. Luckily, if you forget the rules or don't have any picture of this happening in your head, just put it in Desmos and read the end behaviors the way we did it before. Okay? So, end behaviors, patterns for all of our polynomial functions. And then there are some other patterns and just some vocab dealing with what we call turning points. The turning points are also called vertices. Right, if you have a vertex on your parabola, that's a turning point. So it's where your graph is changing from increasing to decreasing or vice versa. Let me show you with this first one, right? Here's a vertex on the graph. If we were reading this from left to right, it is decreasing, decreasing, decreasing until it gets to that vertex, and now it's increasing, right? So this was decreasing, this was increasing. So that vertex is the turning point there, okay? So when the turning point is the highest point on the graph. That means the absolute highest point on the graph. There is no point that goes beyond that point. We call that turning point an absolute maximum. It is absolutely the highest point on the graph. And when the turning point is the lowest point on the graph, there's nothing below it, we call it an absolute minimum. Now sometimes we have turning points that aren't the highest or lowest points on the graph. They're somewhere in between, in which case we would call them either local or relative max or mins. And there's again some patterns that happen with the number of turning points in your polynomial functions. The number of turning points for a polynomial function can be at most one less than the degree for that polynomial. So for instance, if you had a degree of 3, you could have up to 2 turning points. Or if you had a degree of 4, then you could have up to 3 turning points. Or degree of 5, you could have up to 4 turning points, and so on. Okay? Just as an example there. So when I am looking at this number 4, for example, now I know lots of things about this function. Well, we've seen parabolas before, but I know this is going to be even because I know that both of these ends are going up forever, so this tells me that the function is even. And because I have one turning point here, it's probably a degree of 2. Okay, so this is even and it's probably a degree of 2. Now, the focus on the back here was how to describe that turning point. So we have one turning point here on this graph, oops, right here, this turning point, and it is the absolute lowest point on that graph. So we would call this vertex or this turning point an absolute minimum. Okay, now again, looking at number 5 here, I have n behaviors that match. So I know that this is a polynomial function with an even degree and it's got a negative coefficient, and one turning point means probably a degree of 2. Okay, so now this turning point, what kind of classification does it get? Well, this turning point, this vertex, is the absolute highest point on the graph. So we would call this turning point an absolute maximum for the graph. And I can't spell. Maximum. Okay? Number 6. So now what can we tell by looking at this function? Well, because one end is going up and one end is going down, I know that this is going to be an x to some odd power here, and I have 1, 2 turning points. So that means the degree is likely going to be a degree of 3 and a positive coefficient here. So that's just by looking at this, the things that you should be able to identify. Okay, now specifically what we're focusing on is, again, how do we classify these turning points? So we've got a turning point here, we've got a turning point here, right? We're increasing and then decreasing and then increasing. It's where we change. So we're looking for those little hills, the tops and bottoms. Now, this point here is definitely a maximum, right? It's like at the top of a hill, but it's not the highest point on the graph. This graph goes up forever. It has no absolute max. So this maximum point here would be called a local maximum, or we could also call it a relative maximum. I just like the word local better because it's shorter, okay? Here again we have a turning point and it's at the bottom of a hill, so this one we would call a minimum. Now it is not the absolute minimum, right? It is not the lowest point on the graph. This graph goes down forever, so there is no absolute minimum. So again, this would be called a local minimum. Okay? 7. In behaviors are telling me this is an even degreed polynomial with 1, 2, 3 turning points. That means it's probably got a degree of 4, and since both ends are going up, there's a positive coefficient. Now let's classify these maxes and mins. So let's start here. This vertex is at the bottom of the hill, so I know it is a minimum, and it is the minimum, right? There is no point lower than that point on the graph, so we're going to call it an absolute minimum. And then here we have a maximum, but not the highest point on the graph. Since this graph goes up forever, it will not have an absolute maximum, so that would be a local maximum. And then here we have another minimum, but not the lowest point on the graph. We already established the other point was the lowest, so it is going to be called a local minimum. Okay? Here, number 8 is a linear function, so I know that this is going to be an x to the first thing, and there's going to be a positive coefficient here. And how many turning points do we have on it? None, right? We can have at most 1 less than the degree. Well, what's 1 less than 1? That's 0. 0 turning points, right? So this is our linear function. This has no turning points. No turning points, i.e. no max or min. Okay, and then the last one, if you want to give it a shot, by all means, take a pause on the video and then come back. But for everyone else, okay, these end behaviors match. That tells me that this polynomial has an even degree, and it's got 1, 2, 3 turning points, so likely a degree of 4. And because the ends are going down, I know the coefficient of that leading term would have to be negative, okay? Now let's go about classifying here. This is at the top of a hill, so this point is a maximum. Now, is it the highest point on the graph? Nope, there's a higher point, so this is going to be called a local maximum. This next one is at the bottom of a hill, so I know it is a minimum. Not the lowest point on the graph. This graph goes down forever. It is not going to have an absolute minimum, so it's going to be called a local minimum. And then the last one is, again, at the top of a hill. It is a maximum, and it is the highest point on the graph. No point above that one. So this is an absolute maximum. Okay? So you should be able to look at our graphs of our polynomial functions, determine if they're polynomial functions. Either look at the function and tell me what the end behaviors are going to look like, or based on the end behaviors, tell me what the degree is going to be, even or odd. You should also be able to determine if the leading coefficient is going to be positive or negative. And then based on the number of turning points, you could try to estimate the degree. Okay, so lots of things, just reading graphs and determining some characteristics. And that's it for the unit, so make sure you're getting those practices done, and make sure